Hello everyone. Today we are going to talk about Note 12, impact of deductibles on claim frequency. First of all, let's review some of the knowledge we have learned about aggregation payment models. Aggregation payment models we learned said that there are two ways to calculate aggregate payments. One is using the payment per loss, which is YL. You sum them up by all the losses, and the other one is by summing up all the payments. So it's payment per payment. These two will generate the same aggregate payments, but the YL and YP are different. One is payment per loss, and one is payment per payment. And N and M price are different. One is the number of losses, and the other one is the number of payments. The two methods should yield the same result. Therefore, we can calculate the compound mean and variance using either set of random variables. You can have ES, expected value of aggregate payment, to be EN, expected value of N times expected value of YL, or you can have it as expected value of EM prime and expected value of YP. That will be the same. Similarly, for variance, you can use two ways to calculate that. Now let's talk about determination of the distribution of the number of payments M prime. So if the number of losses is modeled by an AB0 class distribution, and it usually is, the number of payments will follow the same distribution but with modified parameters. The parameters are modified as follows. If M is lambda, then M prime will be V lambda. If it's a binomial distribution, parameters M and Q, then for M prime, the Q will become V times Q. Similarly, for negative binomial, the beta will have a factor V there, where V is the probability of loss being greater than the deductible. In other words, V is the probability of a loss resulting in a positive payment. I'm not going to elaborate on how to prove this theory. We are just going to see how we are able to apply this theory to solve the actual problem. But if you are interested in how you prove this, let me know. I can show you. Now let's look at this example. A policyholder's numbers of losses per year follows a binomial distribution with parameter m equal 2 and q equal 0.3. Each loss is subject to a deductible D where the probability of loss exceeding the deductible is 0.8. The number of losses and losses amounts are mutually independent. Determine the probability of a policyholder receiving no payment from the insurance company in a year. First, we are going to just use the regular way we do it to solve the problem. And then we are going to use the alternative solution, where that's what we just learned earlier, the theory of applying the V to the parameter. So let M be the number of losses, then N follows binomial distribution with parameter 2 and 0.3. The policyholder will receive no payment if there are no losses. With the binomial distribution, we can get the Pn0 to be 0.49 using the formula. If there is one loss and loss amount does not exceed the deductible, then we can get this Pn1 times the probability on X is less than deductible, does not exceed. So that's first part of this formula is the probability of loss that is only 1. Then the second part is the probability of loss amount does not exceed the deductibles, which is 1.8%, because the probability of loss exceeding deductible is 0.8, and we can get at least 0.084 to be the number. If there are two losses and both loss amount do not exceed the deductible, similarly, we can calculate the probability of two losses first. Then the probability of the amount does not exceed the deductible will be 1.8 squared, because there are two losses. Then finally, we can calculate the probability of the policyholder not receiving any payment in a year is 0.49 plus 0.084 plus 0036 will be 0.5776. Alternatively, we can utilize what we talked about earlier by applying the factor to the parameter. So here you have the m is the following binomial with parameter 2 and 0.3, and m prime, let m prime be the number of payments. The modified parameter q will be 0.3 times probability of x greater than d, which is 0.8. So you got a 0.24 will be the new parameter. With this in mind, you can utilize the probability of binomial with parameter 2 and 0.24 to calculate the probability of no payment to be Pm prime 0 to be 0.5776. Now let's look at the second example. For an auto insurance policy, the number of claims follows a negative binomial distribution with mean 15 and variance 90. Each claim size is uniformly distributed on interval from 5 to 55. The number of claims and the claim size are mutually independent. A per claim deductible of 20 is imposed. Using the normal approximation, determine the probability that the aggregate payment does not exceed 110% of expected aggregate payment. So to apply the normal approximation, we first need to know the mean and the variance of the aggregate payment. Using the number of payments and the payments per payment approach, we can first get the aggregate payment as to expected to be EM prime times EYP. And variance is this formula 2. The payment per payment of excess loss also follow a uniform distribution. So we can get the YP will be equal x minus 20 condition on x greater than 20. So it follows uniform distribution of 0 to 35. Calculate the mean and variance of the payment per payment. We can get the expected value of payment per payment will be 17.5, and the variance of YP will be 102.08. Then we need to calculate the parameters for the negative binomial distribution. We are given that the expected value of m is 15, so R beta is 15. Also variance R beta y1 plus beta is 90. From this we can get beta is equal 5 and R is equal 3. Now we need to modify the frequency from number of losses to number of payments. probability of x greater than 20 is equal 55 minus 20 over 55 minus 5, which is 0.7%. Therefore, the m prime follow negative binomial distribution with parameter 3 and 3.5, which is 5 times 0.7. From here, we can get the expected value of m prime to be 3 times 3.5 equal 10.5, and the variance to be 47.25. Now that we have all the information that we need, we can use the formula for ES and the variance S to get ES is equal 183.75 and the variance of S is equal 15542.1875. Finally, we can calculate the desired probability as less than 1.1% of ES. Using the normal distribution, we can get it to be 0.5588. So previously, we used the payment per payment method to solve this problem, but we can also use payment per loss to solve it. So similarly, we use the formula for expected value of S and the variance of S. Here we have the expected value of n to be 15 and the variance of n to be 90, and we just need to calculate expected value of payment per loss YL, which is x minus 20 plus. So we can calculate that using the formula, get its expected value of YL to be 12.25 and expected value of YL squared to be 285.833. From this, we can get the variance of YL to be 135.77. With everything in hand, we can calculate the ES and the VARS using the formula. From here, we can also calculate the probability of S less than 1.1 times ES to be the same 0.5586. So here we are just using the payment per loss rather than payment per payment, but you will arrive at the same result. Now let's look at the third example. A collective risk model has a Poisson frequency model with a mean 5 and a severity model as follows. The X has the possibility of 0.2, 0.4, 0.3, 0.32, 0.08 for X to be 0, 200, 300, 1000. Determine the probability that the aggregate loss is exactly 600. So generally, if we look at this case, we can see that S equal to 600 occurs when there are two losses of size 300, or there are two losses of size 300 and one loss of size 0, and or you can have two losses of size 0, and you can also have three losses of 200 or three losses of 200 plus one loss of size 0, so on and so forth. Because there's a size 0, there are many cases, in fact indefinite cases here. So previously we modified the number of losses and payment per loss to the number of payments and the payment per payment by conditioning both frequency and severity on the payments being greater than 0. That is, losses being greater than the deductibles. Using the same logic, we condition both the frequency and the severity on X in this case to be greater than 0. We can get S will be equal I will be the summation of xi, I is equal to 1 to m, or it can be the summation of xi given x greater than 0, and sum it from I is equal 1 to m prime, where m prime is the frequency variable for non-zero losses. So here we talk about how to solve this problem by transform it from payment per payment to payment per loss. Payment per loss to payment per payment. Now let's look at next page to see how it's being solved. So first we need to modify the frequency distribution. Previous is lambda. Now you use lambda times probability of x greater than 0, which is 0.8. So 5 times 0.8 is equal to 4. So m prime follow Poisson distribution with parameter 4. Then in this case, the conditional severity model x can be equal to 200, 300, 1000, with each probability can be calculated to be 0.5, 0.4, and 0.1. And because a loss of 0 is no longer possible, there are only two cases that will yield s equals 600. First case is two losses of size 300. So we can calculate that to be 0.0234. And the second case is the losses of three losses of size 200. We calculate to be 0.0244. Therefore, we can get the probability of s equals 600 to be 0.0479.